The Heisenberg uncertainty principle is one of the fundamental ideas in quantum mechanics. You can interpret it a couple of ways. It can be a limit on what we can actually measure and figure out about a given system, or maybe it's a limit on how much information actually exists at any given moment in a system. So let's look at it. If we imagine, Heisenberg first explained the uncertainty principle in terms of measurement. So that's kind of the traditional interpretation of what it means. But if you imagine trying to find the location of some particle, say an electron we have here, you're going to have to interact with that electron a little bit. And you can imagine the minimum interaction is just having a single photon scatter off of it. And then if we see that photon, we can interpret where the electron was located. Now, there's a couple of things going on. One is that we have a choice of what wavelength of light to use to try to observe this electron. If we have a really long wavelength, then the chances of the photon interacting with the electron are less because it might just not interact at all, kind of jump over it. And so we say the uncertainty in the location of the electron is related to the wavelength of the light that we're using to observe the electron. And we use kind of a funny notation. We use delta x, where it's kind of related to change in, but this is interpreted as the uncertainty in the position of the electron, or whatever we're trying to measure. This principle applies to all things, not just electrons. So uncertainty in x. So that is going to be on the order of magnitude of the wavelength of the light that we're using to observe it. Okay, now we can just have really short wavelength light. That corresponds essentially to high resolution images. But if we have short wavelength light, that means it has a lot of energy and a lot of momentum. And in order to interact with a particle, it might impart a lot of that energy or momentum to the particle. So we'll say that the uncertainty in the momentum, and we'll specify just in one direction because we're going to imagine that we have an initial momentum just in one direction for this light source to kind of simplify things. That's going to be on the order of magnitude of the momentum of the photon, because you could potentially transfer all of the momentum of the photon to the electron. And so the electron could have gained this amount of momentum. And so we have this relation here, these two relations here. And if we combine them and we say, well, the uncertainty in the position and the uncertainty in the momentum is going to be about equal to the product of these things. So wavelength and Planck's constant over wavelength. And wavelength cancels out. So it's about equal on the order of magnitude of Planck's constant. So if I increase my uncertainty in my momentum, so if this goes up, meaning I know less about the momentum, then I can know the position more precisely. I decrease the uncertainty in the position, and vice versa. Now you might think, can't I just measure exactly where an object is, an electron is at a given time, and what its speed is? But if you think about speed, so momentum is mass times velocity, right? If you think about the velocity, that inherently depends on a time interval. Velocity is, if it's a constant velocity, it's delta x over t. Well, if I look at it at one moment, I'm going to disturb where it's going to be at the next moment. So I don't know what its momentum was before I interacted with it. So there are limitations to measuring both of these two things. You can't know both of them exactly precisely at the same time. Okay, another common uncertainty relationship has to do with time and energy. So if we think about the time that this photon is interacting with our electron, it's going to, the time it takes to travel the uncertain distance or the uncertain location is going to be delta x over c, because it's going speed of light. This is just delta x equals vt, right? So this is the uncertainty of when we made the measurement. It's related to the uncertainty of where the object was when we made the measurement. Okay, and the uncertainty in delta x was approximately lambda wavelength over c, so we have this relationship. Okay, now if we transfer the energy, or think about the energy transfer to the electron rather than the momentum, well, the energy of the photon is hf, and so it could have transferred, all of the energy. It might not have transferred that much, but it could have transferred that much energy to it. And HF, if we write it in terms of wavelength, that's hc over lambda. So we play a similar game here where we multiply the uncertainty in the energy by the uncertainty in the time when it had that energy. And we're going to get approximately hc over lambda times lambda over c. And amazingly enough, we also get that the order of magnitude of the product of those two uncertainties is h. And again, the more we know about when we measured the energy, the less we can know about what energy it had. And it turns out if you do a more rigorous derivation of these relationships that you get that the uncertainty is a little bit less than h. It's Planck's constant divided by 2 pi. So this is a number greater than 1, so it's a little bit less. And it can be greater than that. This is just the lower limit on the uncertainty. I mean, we could know absolutely nothing about either of these things, so it's between Planck's constant over 2 pi and infinity, I guess. You could have infinite uncertainty. This quantity right here comes up so often in quantum mechanics that they actually come up with a new symbol for it. They call it h bar. It's also known as the reduced Planck constant, and it's just equal to that, which works out to be 1.055 times 10 to the negative 34th joule seconds. So you might want to jot that guy down as well, because we're going to use this quite a bit. All right, let's look at a couple of examples. We've got an electron. We know its speed to a given precision, and we want to know how precise we can know its position simultaneously. So we're comparing the uncertainty in these quantities at the same moment that we're trying to measure them, right? We could know the speed precisely at one time and the position precisely at another time, just not at the same time. All right, so first thing we need to do is find the momentum of this thing, because our relationship is delta x and delta p, not delta x and delta v, right? So this was approximately equal to h bar. We'll just go ahead and use that notation now. So P is equal to mv. We're just using our regular standard classical momentum formula here, because this velocity is not very near the speed of light. The mass of an electron is 9.11 times 10 to the negative 31st kilograms. And then we multiply it by this velocity, so 1.1 times 10 to the 6th. So we get an overall momentum of 1.00 times 10 to the negative 24th. Now we're not interested in the overall momentum, we want the uncertainty in the momentum. Okay, again, don't interpret this as change in momentum necessarily, but as uncertainty in momentum. And it was 0.1%, so that's this number times 0.001, which just changes our exponent there, right? So 1 times 10 to the negative 27th now. Okay, now we can plug that in over here. If we rearrange and solve for the uncertainty in the position, we're going to get h bar over the uncertainty in the momentum. So h bar was 1.055 times 10 to the negative 34th, divided by this uncertainty here that we found, 1 times 10 to the negative 27th. And that works out to be 1.1 times 10 to the negative 7th meters, which seems pretty small, but this is about 1,000 times the diameter of an atom. So on the subatomic scale, this is a fairly large distance. If we know the speed quite precisely, then we really don't know exactly where the position of this is. There's no way we possibly could know it more accurately than this. This is the best we could possibly do. All right, one more example using energy stuff. If you remember back when we did particle physics, we actually used the uncertainty principle, and I mentioned that we would eventually get to explaining it, and so here we find the R. But we related the lifetime of a particle, an unstable particle, to the uncertainty in its mass. We had those resonance width things where we were measuring the energy here that was related to the mass of the particle. Anyway, so now that we've got the uncertainty principle and understand it a little better, we can use this. we're going to use uncertainty and energy. Now here we want the uncertainty and mass, but we can relate mass and energy, right? So first we're going to look at the uncertainty and the energy, then we're going to relate that to the mass through E equals mc squared. So uncertainty and energy and uncertainty in time is on the order of h bar. So if we rearrange this to solve for uncertainty and energy, it's just h bar over uncertainty in time. And we tend to ignore the fact that the uncertainty can be greater than this. So we just say, okay, this is the minimum uncertainty we could have, when we could always have more uncertainty than this. All right, so we plug in our numbers here, 1.055 times 10 to the negative 34th. The uncertainty in time. So this is the average or mean lifetime, but it could decay kind of anywhere in that range. So we just consider the mean lifetime to be the uncertainty in the time. So 2.91 times 10 to the negative 13th, and that gives us an uncertainty in the energy, 3.625 times 10 to the negative 22nd joules. And so if we kind of rewrite E equals mc squared, c squared we're going to say is pretty well known. So the uncertainty in energy is related to the uncertainty in the mass. So to get the uncertainty in the mass, we just take the uncertainty in the energy and divide it by c squared, which is easy enough to do. So 3.625 times 10 negative 22 over 3 times 10 to the 8th, because that's the speed of light, right? And since these are all SI units, this is joules, this is meters per second, we know that our units will come out to be kilograms, because those are SI units of mass. So 4.028, guess I should have rounded a bit, but this will work, times 10 to the negative 39th kilograms, which is quite small. Another way we can express the uncertainty in the mass, or just masses in general for particles, was EV per c squared, if you remember doing that again with particle physics. So doing this a different way, we can convert this uncertainty in energy to electron volts. So I can say 3.625 times 10 to the negative 22nd joules, and then I multiply it by the conversion factor of 1 electron volt per 1.6 times 10 to the negative 19th joules per electron volt. So this gives me an uncertainty of 0.00226 electron volts. So that's kind of a pain to have to remember this conversion factor. But once you have the uncertainty in the energy in electron volts, the uncertainty in the mass, one of the units of mass is EV per c squared. So we don't even have to plug in the value for c. We can just say it's 0.0226 electron volts, and then we divide the c squared over, and we just leave it in terms of c squared, because those EV per c squared are mass units. So this is another way to express the uncertainty in the mass, which is equivalent to that if you convert EV c squared to kilograms. So, all right, there you have it, the uncertainty principle.